Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Muhammad Firdaus bin Muhammad Zali, and today I would like to present about the assignment digital communication system. And first of all, I will explain about the block diagram. So, the main purpose of the system is to synchronize the frequency and phase of the received signal with a local reference signal. So starting from the input, the incoming signal may contain frequency and phase offset due to differences between the transmitter and receiver oscillators. This means the received signal is not perfectly aligned with the local carrier. So the signal then goes to phase, this phase frequency detector, or we call it PFD, which compares it with the feedback signal from the voltage control oscillator, or we call it VCO. So the PFD detect both phase and frequency differences and produce an error signal based on the mismatch. So this error signal is passed through the PI loop filter. PI means proportional integral. The loop filter smooths the signal and generate a stable control voltage. So the proportional part improves response speed, while the integral part removes steady state error. Next, the control voltage is applied to the VCO, which adjusts its output frequency and phase accordingly. The VCO generates a local signal that continuously tracks the incoming signal. So the VCO output is then fed back to the PFD, forming a closed loop system. This process continues until the frequency and phase differences are minimized. Once the system reaches this condition, the PLL considered locked, meaning successful synchronization has been achieved.
My name is Synchronization, and this is my MATLAB code, which has four main parts: parameter, signal generation, the PLL loop, and plotting. First, we will set the sampling frequency to 20,000 Hz, duration 0.4, and carrier its frequency is 150 Hz. I also add a 15 Hz frequency offset and a 60-degree phase offset. For PLL gains, I choose KP 0.8, KI 0.05, KVCO 80 for fast locking and stable operation. So inside the loop, the phase frequency detector compares input and VCO edges. If the input edges come first, error is +1, means VCO lagging. If VCO edge come first, error is -1, otherwise 0. So this error is smoothed by a low pass filter with alpha 0.1, then integrated. The control voltage is Kp times filter error plus Ki, the integrator. Finally, the VCO phase updates using the numerator frequency plus KVCO times the control voltage. This generates the next VCO output, completing the loop.
My name is Lau Junhong. Now I will run the simulation. Graph 1 shows the unsynchronized signal. The red wave drove away from the ideal black dasher carrier due to the 15 Hz frequency offsets and start at a different point due to 60-degree phase offset. This shows why synchronized is needed. Graph 2 shows the synchronized result. The blue recovered carriers perfectly overlap the black dasher ideal carrier with no drill and no shift. This proved my PPL achieved both frequency and phase synchronization. Graph 3 shows phase error convenience. It starts at 60 degrees and drops exponentially to near zero by 100 to 150 milliseconds, staying there. The red dasher line marks perfectly locked. Graph 4 shows phase profiles. The blue through phase increased linearly. The red VCO estimated phase catch up and become parallel to the blue line. Parallel means equal slopes, and equal slopes means matched frequencies. This is key evidence of frequency synchronization. In conclusions, all four graphs prove my PPL successfully synchronized frequency and phase. Thank you.